Yeah, one of his poems is like about.
All right, here's some examples of how to do some math problems with this equation. Ready?
Yep.
So work equals force times distance. Now I use the whole push something with a boot thing, but there are lots of different ways that you can apply a force. Let's say that I am pushing an object with just enough force to overcome friction. So this sliding force will be the force to overcome friction. Got it? Coefficient of friction is 0.4. Let's make the mass 2 kilograms. And I push this just hard enough to overcome friction, and I'm going to push it 2 meters. Okay? How much work is done? So this equation then just becomes the force to overcome friction times the distance, times 2 meters. All right? So the force work is force to overcome friction, which if you look at the board, what should I substitute for force to overcome friction? Mu times the normal force times the distance. By the way, that, you just came up with an equation for work to overcome friction. We'll add that too. We're going to start a list of energy equations. So if we put the numbers in for this, the energy that it took to overcome friction and move this 2 kilogram block 2 meters would be mu times the normal force. What's the normal force in this picture? 19.6. That is correct. 19.6 newtons is the weight of the object. So 2 times 9.8. And the distance we pushed it was 2 meters. What did you get? Did somebody already type this in? 50. Okay, 2 sig figs? 16 units. Joules is correct. Okay, so that's one type of problem. Let's do something else. Let's say that now our 2 kilogram mass is on a frictionless surface, so mu equals 0. And I'm going to push it 2 meters again. But this time, I push it with a 10 Newton force that's oriented at a 15-degree angle to the horizontal. So for energy or work, you always use the force in the direction of motion, which is going to be the horizontal component of this right triangle. Who can tell me what this component is in terms of 10 and 15 degrees? 10 cosine 15. See how easy this is now? So that becomes our force. So 10 cosine 15 is the force. 2 meters is still the distance. We don't even care about the mass at this point, right? So work equals force times distance, 10 cosine 15 times 2. That will change, however, if I throw in some friction. That will change if I throw in some friction. Now the weight becomes important, right? Because that's part of the normal force. But that's not the only thing that impacts the normal force. What else would impact the normal force? Yeah, this right here, this force. So we have 19.6 newtons plus, what would we label this vector as? 10 sine 15, right. Now this is where the positive and negative sign becomes important, okay? The total work will be equal to work push and work done by friction. Now, most of the time, we want stuff to move. Move that block, I say. Move it. So is push work good or bad? Good. That's a positive work. Friction, bad. Most engineers spend their careers trying to reduce friction, trying to make systems more efficient for human use. Matt?
So is this work push minus work friction, or?
Yes, that is correct. Work push minus work friction. So then the total work would be, and see if you can follow this, work push, that didn't change. That was originally what we calculated. So 10 cosine 15 times 2 meters. And work done by friction is, from this formula up here, mu times the normal force times the distance, right? So that would be 0.1 times the total normal force. Who can tell me what that would be? 19.6 and plus 10 sine 15, right. So that's the total normal force. And the distance is still 2 meters. So if we do all that, ruh-roh, we end up with, let's see, I ended up with 7.2 joules of work. Nice thing about this is, if you're careful with your parentheses on your calculator can do this correctly in terms of order of operations. So you can do all that math basically in one step. You can punch that all